Hello audience. Today we will discuss EMC challenges in Advanced Driver Assistance Systems, ADAS. ADAS usually facilitates safe driving and can provide the driver with an alert if the system detects risks from surrounding objects such as errant pedestrians, cyclists or even other vehicles on an unsafe trajectory. It is the increasing focus of consumers on safety, demands for comfort while driving and the continued increase of government safety regulations that are main growth drivers of ADAS in automobiles for the latter half of this decade. ADAS technology also features many elements in common with autonomous driving, AD, technology. Current radar systems operating at 24 GHz, K-band, are prevalent in new vehicles with ADAS systems, and there will be an inevitable shift to state-of-the-art 76 to 81 GHz radar systems to support autonomous vehicles. These systems already present EMC challenges that must be addressed at the board level, intra- and inter-vehicle levels, and signal processing level. Given the EMC and EMI challenges that arise within a single radar module, between radar modules, and between multiple vehicles, how can systems designers ensure multiple nearby vehicles can be sufficiently resolved by an autonomous vehicle? Here, we will look at the current EMC challenges that arise in vehicles with frequency modulated continuous wave systems and some future directions systems and board designers can take to overcome these challenges. Current automotive radar EMC challenges. Moving to the 76 to 81 GHz range provides a number of benefits compared to K-band radar. These include broader available band fault width, lower attenuation, more focused beams, and longer range. As is well known, moving to higher frequencies increases onboard crosstalk and radiated EMI. As newer vehicles will use multiple module for long-range and short-range radar, as well as wireless systems at other frequencies for vehicle-to-everything communication, there are some particular design challenges that systems designers should consider to ensure proper target detection. Particular EMC problems become more apparent as multiple radar-equipped vehicles occupy roadways. Mixed signal interference. This is primarily a board-level challenge that requires proper stack-up design, layout, routing, and grounding techniques. In newer commercially available 24 GHz and 76 GHz radar modules, you will find that the digital and RF sections are sometimes separated into different boards within a single module. This requires proper grounding, routing, and layout to prevent EMI between analog and digital portions of the module. Separating digital and analog sections into different boards is a natural choice as it does not significantly increase the footprint while it effectively allows you to have two stacked signal layers, analog and digital, on different boards. Some current radar modules use coplanar waveguide routing on the surface layer to the transmission and reception series fed patch antenna, SFPA, arrays to provide sufficient high-frequency isolation from other sections of the board. Multiple vehicles operating in the same frequency band. This is a major EMC challenge in automotive radar design, which arises when multiple vehicles with radar operating in a similar frequency range interfere with each other, which masks detection of any true targets. Radar will also cause multiple false targets. The logic here can be extended up to any number of vehicles. The effects of radar congestion in multiple scenarios, and the results provide significant insight into the effects of interference between radar modules on different vehicles. This particular EMC challenge is difficult to solve at the PCB level, but it has been addressed at the signal processing level. This is the same EMC challenge that occurs with K-band radar emitters used by Department of Telecommunications to monitor real-time traffic flow in many major cities. The current solution involves placing an anti-aliasing filter on the reception side of the signal chain before the signal is sampled with an analog to digital converter. Distinguishing multiple targets. Once false targets from other interfering radar systems are suppressed, the true targets need to be sufficiently resolved. This is primarily a pulse design and signal processing challenge. In terms of pulse design, a designer needs to try and maximize the detection resolution while balancing maximum unambiguous range and velocity. Systems designers require selecting the appropriate components that are robust against some common signal integrity problems in RF systems. Suppressing intermodulation products. ADAS designers need to be familiar with passive intermodulation, and the same effect can occur in amplifier stages used in RF signal chains for frequency modulated signals. The third-order intermodulation products are the most important as they lie closest to the FMCW band fault width, although other odd-order products will be present and can lead to interference in wideband signal chains. As higher frequency, radar systems use relatively wideband amplifiers and analog-to-digital converters, intermodulation products can propagate into the receiver side as crosstalk and reduce the usable range in a radar module system. This is particularly problematic with power amplifiers on the transmitter side, which typically run near saturation. This is another problem that should be addressed at the board level and circuit level. A higher order filter on both sides can be used for intermodulation product suppression, while eliminating interference requires sufficient isolation between the transmitter and receiver sides of the RF signal chain. The future of automotive radar. Although we already looked at the signal processing and layout challenges in automotive radar systems and modules, we still have not considered EMI from the rest of the vehicle. Strong electromagnetic fields in electric cars leads to EMI that increases the noise figure in an FM continuous wave radar module, which can reduce the maximum available range based on the required signal-to-noise ratio value. At the radar module and ECU levels, all signals required for MIMO radar must be phase and frequency synchronized so that a coherent beam can be constructed for angular resolution with a phased array antenna. In the process of locating and tracking vehicles in the nearby environment, a significant amount of data gets generated and must be sent to an ECU. Sending these data throughout a vehicle with coaxial or twisted pair cabling incurs losses and makes them susceptible to high-frequency EMI from other systems. Using fiber with radar systems is a natural choice, that is, radio over fiber, to eliminate susceptibility to EMI within a vehicle. This particular EMC challenge is currently being solved primarily with signal processing, appropriate component selection, and layout to produce accurate angle resolved range and velocity estimates for nearby vehicles. Obviously, any new millimeter wave system must pass EMC checks before it hits the market, and generalized in-lab test procedures are being developed for evaluating high-frequency automotive radar systems. The next advance in automotive radar might come in the form of partially coherent radar systems. Thanking you.